Hi, Year 13. This is your first remote lesson for maths. In this lesson today, for Monday, we're going to be doing a bit of recap for differentiation because we've nearly finished the chapter for differentiation, and it's worth us getting really good at these methods and techniques that we've learnt before we move on to integration, which a lot of which involves doing these things backwards. Okay, so I'm going to go through these top 3 examples on this first page, and then I'm going to leave you to do the rest of the questions down here, which are going to be similar. The answers are attached as well. I'd like you to, once you've finished, mark it, make sure that you know you're getting them right, and then you can submit them to me online. Okay, so starting off with these top 3. If you've got your list of derivatives and your 3 main differentiation methods that we know, which is the chain rule, the product rule, and the quotient rule, it'll be helpful to have those handy for you to look at as I'm going through these. Okay, so I'm going to dive right into the first one. So the first question just wants us to work out some derivatives, just work out dy by dx. So looking at the first one, I can see that that's just going to be mainly applying the product rule because these 2 functions I'm going to highlight are multiplied together. Then you're going to look through your list of derivatives to work out what these differentiate to, but also notice that each one has got its own chain rule inside because the inner function is 2x and 3x rather than just x. So to differentiate, I'm going to write down the method I'm going to use, not R, I'm going to use P. Right, product rule, dy by dx then. So start off then, differentiate the left side, the blue function. Well, an exponential goes to itself, but the inner function from the chain rule will give us a timesing by 2. So that's the differentiation of the blue. Then I'm going to keep the red function the same, sine 3x is the same. Add in between, and then other way around, so I'm going to leave the blue function as it is, e to the 2x, and then differentiate the red function. Sine differentiates to cos, so I'm going to write cos first of all. I'm going to keep the inner function the same from the chain rule, but then this inner function has a derivative of 3, which is going to come out, and I'm going to put it right at the front. Okay, so that's done. There's no simplifying there. I guess I can factor out e to the 2x if I wanted to, but that's enough to show the derivative there. Okay, part B. This is a function inside 2x squared plus 1, and that's all raised to the power of 5. So that's going to be one big chain rule, is the main component of what we're trying to do. Okay, so this one, I'm firstly going to highlight which function is which. The inner function I'm going to put in red, so that's the bit in the bracket, and the outer function is raising that to the power of 5, so I'm going to put that in blue. Right, so what the chain rule says then? The chain rule says you do the outer derivative first, keeping the inner bit the same, and then you multiply that by the derivative of the red. So the blue function, raising to the 5, is going to turn into 5 at the front, and then the power goes down by 1. So that's the blue bit done. The red bit stays the same. But then out of the inner function, we get its own derivative, which is 4x. Okay, so all of that put together, I can combine the 4x with the 5 and write it as 20x. And then this 2x squared plus 1, and that's to the 4. Okay, and that one's done. Right, so that's just a recap of using 2 of the 3 rules that we've used. Don't forget the quotient rule as well. The quotient rule being, I think, the only one that's given in the formula book. Okay, right, example 2. So we have done a lesson on doing these with parametric equations. You can still get the gradient of that, and we're going to use it to find the equation of the tangent at the curve at the point when t equals a half. Right, so let's see what we've got as well. We've got x is 4 over t, and we've got y equals 4t, and t is non-zero to stop us having x being undefined. Right, so if I need the equation of the tangent has gradient dy by dx. Which I can get using the methods that we've done for that. And if I want its equation, the gradient is a good thing to know, but also a point is going to be useful as well. If I know that, I can then work out its equation. All right, so let's do the gradient first, dy by dx. Now, if you remember, if your curve is defined parametrically, then dy by dx is dy by dt divided by dx by dt. Okay, the idea being that the dt's on this right side kind of cancel out, leaving the dy on the top and the dx on the bottom. Okay, so what's that going to be? Well, the top is the easy one because it's just for t, for y. So I differentiate that with respect to t and I get 4. Then on the bottom, I can differentiate the x's with respect to t as long as I recognise it as 4t to the minus 1, which differentiates to minus at the front becomes minus 4, and then that becomes t to the minus 2. Okay, so I'm going to put that down on the bottom there. I'm going to put the minus at the front, and then I'm going to put 4 over t squared because that's t to the minus 2. Right, so I now want to tidy this up a little bit, don't I? I can cancel out the 4 and the 4, leaving 1 and 1. But then because I've got this nested fraction as well, I probably want to times by t squared on the top and bottom as well. And that's going to give us t squared on top, minus on the outside, and then that was a 1 over t squared, times it by t squared again, gets you back to 1. So all in all, you've got minus t squared. And that's dy by dx. Okay, so that half of this is done. To get the point, I know a t value, so I can use that to work out x and y tell me my coordinate. So when t is a half, I can work out x. X is 4 divided by a half, which is 8. Y is 4 times t, 4 times a half, which is 2. And the gradient is given by minus t squared, that's minus half squared. Half gets squared first, then becomes negative, so it's minus a quarter. Okay, so these are the 3 numbers that I need to work out the equation of my tangent. I'll write down the formula for it to remind you. So y minus y1 equals m x minus x1. That's my point gradient formula. And then you stick the numbers in. So y minus, and then the y coordinate is 2, equals m is minus a quarter. And then the x value is 8. And then hopefully that's going to tidy up and end up looking like what we've got over there, what we're trying to show. So let's start by timesing everything by 4 to get rid of the quarter. So now 4y minus 8 equals, and then the minus stays still there, but I'm going to distribute it across this bracket to get rid of the brackets, so it's going to become minus x and then plus 8. Okay, and then not hard to see where to go from there to get it to look like this. I'm going to keep the 4y, I'm going to add the x to the other side to make plus x, and then I've got plus 8, and I'm going to add this 8 to it as well. And then you're done. Okay, this example 2 is finished. So that's the equation of the tangent. For the third one, I'm going to clear all my annotation first of all. Okay, so example 3, it looks a bit more complicated because of how the function looks. So this is a curve defined by 2x plus y equals x plus y all squared. Now this is one of the ones where it's impossible to isolate y or x on its own. So what we have to do for this one is treat y as a function of x and then do implicit differentiation, okay? Because our curve is defined implicitly, not explicitly. So if you remember doing this, so y is just some function of x that we don't know what it is because I can't rearrange it. But whenever I see a y, I can just treat it as a function of x and use the chain rule to get its derivatives out. So what I'm going to do now, I'm going to highlight the 3 terms that I've got separately so I can refer to them. So I've got that in red, I've got y in blue, I've got the right hand side in pink. And then I'm going to differentiate all 3 things. And remember, if I see a y, I can use the chain rule to get its derivatives out. So 2x, that has no y's. I can just differentiate it. So that becomes 2. Y is a function of x, and I differentiate it, and that's going to become dy by dx. And then the right hand side, well, this is going to be a chain rule because it's an expression that I've got with x's. Y is a function of x as well, and then that's all squared. So I'm going to use the chain rule to work this bit out. So to do that, the 2 is the outer function. That's going to come to the front and drop down to become 1. So this is 2 times x plus y to the 1, which I'm not going to write. But then I need the inner function as well by differentiating what's in the bracket and multiply by that. So x plus y differentiates to, x goes to 1, and y is my unknown function of x, which goes to just dy by dx. Like that. Okay, so that's everything differentiated. I've now got to isolate dy by dx and hopefully show that it equals this expression on the right. So I think to proceed, we're going to expand the brackets on the right hand side. I'm going to change to black as well. So 2 plus dy by dx equals 2 times, okay, expand the brackets, x plus x times dy by dx is the outer bits. The inner bits makes y, and then the final bits makes y dy by dx. Okay, now I'm going to expand out the 2 and start to collect things together. So 2 plus dy by dx is 2x plus 2x dy by dx plus 2y plus finally 2y dy by dx. Okay, so now everything's expanded out. I can see the dy by dx terms that I need to collect together, and I think the best thing to do is to collect it on maybe the right hand side, because then most things are positive, but we'll see what happens at the end. And then the 2x and the 2y I'm going to collect on the left. So rearranging gives me 2 minus 2x, that's this 2x, minus this 2y equals dy by dx multiplied by, and then I've got this 2x of them here, I've got this 2y of them there, and then I've brought this minus one of them back as well, so minus 1. Okay, so that's factorised. Then to get dy by dx on its own, you divide this bracket underneath. So it's 2 minus 2x minus 2y over 2x plus 2y minus 1. Okay, so that's everything rearranged to one side, but I've got to now try and get it to look like what I've got over here. It doesn't quite look the same, except if you try and factorise it, you can see how it's meant to work. So what I'm going to do is I'm going to factor the top, remove the bin. So this becomes 2 lots of 1 minus x minus y. And on the bottom, it's very suggestive over here to factor out this 2 from the x and the y, so I'm going to do that. 2 times x plus y minus 1. Okay, so now we've got to think about how this is different from what we've got. Well, if you look closer, you'll notice everything on this side is the negative of what I've got written down here. So if I make the top portion negative, then all of these signs will flip, making the right numerator. And if I swap the order of this subtraction, I can make the bottom negative as well, which makes what I've got over here. So I'm going to do times minus 1 times minus 1. And that will give me exactly what I want. So let's see if I can fit it in. So it's 2, and then minus x becomes x, minus y becomes y, and 1 becomes minus 1. And then if I swap the order over, minus 1 becomes 1, and this becomes minus 2, x plus y. Okay, finished. Right, that's dy by dx shown. Now it wants to do the coordinates of the stationary points. So if you recall, so this is stuff we've done from year 12, stationary points are when dy by dx equals 0. Okay, I've got an expression for dy by dx, so I can just set that equal to 0, so I'm going to do that over here. Right, so what have I got? 2x plus y minus 1 over 1 minus 2 x plus y equals 0. Now, because I've got this fraction equaling 0, the only time that happens is when the numerator becomes 0. So I can now exclude the bottom bit, just focus on the top. So actually, we've just got, well, I can take away off the 2 as well, can't I? I can divide by 2 because that's not 0. So it ends up being x plus y minus 1 equals 0. So that describes where I can find the stationary points. I've now got to use that information to work out some coordinates. So I've now got to link this expression here with the curve itself, which is right at the very top. So to do that, I'm going to rearrange this first of all. I'm going to get y on its own. So y equals, and it's going to be 1 minus x. Okay, that's a rearranged version of that. I'm then going to plug that back into my original curve, and that's going to give me some equation that just has x's in. So I'm going to sub into C. Right, so let's write this again, but replace all the y's. So I'm going to do that over here, actually. I'm going to star over here, I'm going to go over here to get some space. So what have I got? 2x plus, and then y is 1 minus x. And then that equals, right, x plus, and then y is another 1 minus x, and that's all squared. Okay, so that's substituted in. Tidy up, so 2x plus 1 minus x is x plus 1. And then if I tidy this up, x plus 1 minus x is 1, and 1 squared is 1. Okay, so that's given me something I can solve for x. X plus 1 is 1, take off 1, x is 0. And all I need now is to work out what y is if I can go back to here, can't I? I can go back to this box here. Y is just 1 minus x. So y is 1 minus 0, which is 1. Right, so the stationary point is 0, 1. And that's my final answer. Right, finished. That's quite a lot of methods that we've used. We've pretty much covered them all. The only one we haven't is quotient rule, but I'll leave that to you. You've got the notes for how to do that. So if you'd like to have a go at the questions underneath then, and mark it once you've done, and I'd like to see how well you did with that. Okay, so these ones here, if you need any help at all, please feel free to let me know. There's some bits here that are involving other topics that I've seen, like partial fractions. I don't think you can differentiate that yet until you've done partial fractions, then that makes it a bit easier. Okay, right, so I'll leave that to you to do. Thanks very much, Year 13. Enjoy yourself, and I'll see you soon.